Hey guys, we're up to 8H, which is recurrence relations to model growth and decay. Before we get into any new stuff, I want to look at recurrence relations again because I think a few people are a little bit confused about them since I sort of explained it last time. Now, when I was explaining it last time, and this is a recurrence relation here written in blue, I explained it as the next term, as in this bit meant the next term. This bit here, I think I said the term before it, and this bit here means the common difference. I didn't really talk too much about n and the numbers there as well, so I want to kind of give you a little bit of an example there. So let me just start with perhaps a term that we know. So the term that we're up to currently might be Tn. I don't know exactly what term that is. But if we add the common difference, as it says up here, so plus d, if you're on a certain term and you add the common difference, that's going to give you the term before it. Now, the next term, sorry. So the next term, if we're currently on Tn, the next term is going to be Tn plus 1. The next term. Now, let's use some actual numbers here. So if we're up to, let's just say the second term, so T2, and we add the common difference, that's going to tell you T2 plus 1. Now, instead of writing 2 plus 1, that's T3. So T3 equals T2 plus the common difference. Now, let's just do it again with another example. If we're up to T50, we know about T50. And if we add the common difference to T50, that gives us T51. So that's what these recurrence relations are showing us, and they actually look a bit more complicated than what they actually are. Okay, now the two things that they're actually showing us are the common difference, which is whatever's here. So this bit here is really important. And they also tell you over here, perhaps, often they tell you the first term, but they might just tell you any term within the sequence. So this bit over here is really important too. So this bit here, they tell you the common difference. And this bit over here, they tell you normally the first term. I'm going to say first term here. And if you know the first term or any term, and you know the common difference, you're going to be able to keep adding the common difference to get the next terms. Or if you want to go backwards, you just take the common difference away. Let's do an example though, before we move on to the new stuff in 8H. All right, so it says, use the following recurrence relation, which we've got just here, to find the first 5 terms of an arithmetic sequence. So again, we've got our first term here, and we've got our common difference here. Now this is saying your next term is equal to your current term plus 200. So if our current term is 1000, our next term, to get there, we add 200. So it's going to be 1200. Not 1200, just, yes, 1200. All right, now if 1200 is our current term, to get to our next term, we add 200. There we go. We add another 200. We add another 200. Do you see how we now have 1, 2, 3, 4, 5? Our first 5 terms, and we got that by using the recurrence relation because it tells us a term and the common difference. So we're going to use that today when we focus on some more stuff to do with growth and decay. All right, so now for the new stuff. So 2 of the key words that we're going to hear in this chapter or exercise are growth and decay. Now, I think we probably already know what they mean, but in terms of numbers, growth would mean your numbers getting larger. Decay would mean that your numbers getting smaller. Okay, now this is pretty much what we're going to be doing. So using a recurrence relation, which we looked at just before, to model linear decay. So we're mainly going to be looking at numbers that are going down. And flat rate depreciation. So you may have heard the term depreciation before. It means the drop in value. So again, we're looking at decay, but particularly when we're talking about money, depreciation is one of the terms that's used. And flat rate, that just means that our value is going down at a constant rate. So if it goes down $100 the first year, it's going to go down $100 the second year, the third year, and so on. Okay, so that's what I've got written down there anyway. All right, so let's do a bit of an example surrounding that. All right, so below is a recurrence relation modeling the flat rate depreciation of a car. It depreciates at a flat rate of 10% of its original value per year. Okay, so let's look at this recurrence relation. It's telling us that the original price is $10,000. It hasn't told us that it's measured in dollars, but it is. And this relation over here is telling us that it's going down 1,000 each year. Okay, now it told us before that the flat rate of 10%, hopefully we know that 10% of 10,000 is 1,000. That's why it's going down 1,000 per year. So let's look at A. Fill in the table below showing the car's value each year. Okay, so let's go through and try and fill this out. So we know that it's going to go down by 1,000 each year, don't we? So the depreciation, no matter what year it is, whether it's like when we start, which would be year 0, the end of the first year, the end of the second year, the end of the third year, the end of the fourth year, doesn't matter when it is, our value is going to go down 1,000 every single time. It's going to go down the common difference. Awesome. Now, V0, so the value right at the start, we were told was 10,000. There we go. Now, if we are depreciating 1,000, that means our next value is going to be 9,000 at the end of the first year. If we're going down, we go into the next year and we go down another 1,000. At the end of the second year, it's going to be 8,000. At the end of the third year, it's going to be 7,000. At the end of the fourth year, it's going to be 6,000. So hopefully we can see that it's just going down by the same amount, which is 1,000 or 10% of the initial value each year. Now, what we can also do, and we've done something similar to this before, is come up with a rule to help us find the nth term. So if we want the 100th year, we'd make n100. If we want the 50th year, we'd make n50. Now, there's a rule here. There's actually two. They're slightly different. So if you're dealing with growth, this is what your rule is going to look like. So that's the value of whatever term. If n's 100, n would be 100 there, n would be 100 there. D is our common difference, and V0 is our value at the start. But we're looking at decay here, aren't we, with our example. So this is the rule that we're going to be using. All right, it says write an equation that will predict the car's price in the future. So we can use this one. So the value of the car, value at n, whatever year that is going to be equal to the value at the start. We were told the value of the start was 10,000. And it's going to go down, whatever the value of n is, we leave that as it is, times by the common difference, so, or how much we depreciate by. So we worked out that we were depreciating by 1,000 each year. So this rule here should help us find the value of that car for whatever value of n we're looking for. Now let's just use this example here, C, this question here, to see if the rule actually works. So find the value of the car after 4 years. With this table up here, we already worked out the value of the car after 4 years was 6,000. So let's use this rule and see if we get the same thing. Okay, so we want the value of the car when n is 4. Okay, so we change n to 4. All right, now we still have 10,000 there, minus we change this n to 4 as well. All right. So the value after 4 years is 10,000 minus 4 times 1,000, so that's 4,000. So our answer is 6,000, which is the same as what we had up here. So if we wanted the value after 100 years, you could put 100 in there and you can work it out. Okay, so that should work with any scenario that you're given. There's a worksheet for you guys to have a bit of a look at, so you'll find that attached to our lesson instruction.